This is Lewis structures. Okay, named after a scientist by the name of Gilbert Lewis. And I just want to preface this by saying all molecules have a 3D shape and geometry. Okay, and we're going to focus on covalent compounds. What is a covalent compound? It is a nonmetal with a nonmetal. So covalent compounds is nonmetal with nonmetal. Bless you. And what else does covalent compounds mean? What's happening with the electrons? Are they being transferred or sharing, David? He's absolutely correct. Okay, they're sharing. So this is where we're going to be talking about double bond, single bond, and yes, even sometimes a triple bond. So this is a sharing of electrons. Okay. All right, are you ready to play this game? Okay. Ready? All right, so we're going to start with some rules, okay? We're going to start with some ground rules. From those rules, this is not rules that, they're just a small set. There's many, many rules. I'm only going to give you 5 or 6. From these 5 or 6 rules, we're going to build structures. We're going to build the geometry of the molecule, okay? Just realize I'm only giving you 5 or 6. There's actually, I don't know how many, okay? So let's begin with ground rules. Okay, we need to follow these rules, and they're a little bit complicated, but hey, any type of game is complicated. I bet the games you play are really hard. Okay? I grew up with Nintendo, 8-bit Super Mario Brothers, The Legend of Zelda. Oh, and when they had the Sega Genesis, I was like, wow, that's insane, the graphics. All right, the first rule here is carbon. Carbon loves 4, or carbon is happy at 4. Okay, in fact, carbon is not just happy at 4, carbon loves 4. Loves, okay? Carbon loves 4. So this is what I mean when I say carbon loves 4. All right, I'm going to draw my carbon. Okay, you can count with me. 1, 2, 3, 4. Another thing in this section, I need you guys to count. Okay, yes, counting. Counting is very important. Okay? We learned counting in preschool. I think my kindergartner doesn't know. She knows 1 to 20, I think. But counting. All right, so count with me. 1, 2, 3, 4. Okay, 4. Okay, so this is 1 electron. This is called a valence electron. This is 1 electron. This is 1 electron. This is 1 electron. Okay, I'm going to make this so that it's ready to form a bond. Okay, that 1 electron is ready to form a bond with someone else that's going to give that electron. Same thing here, ready to form a bond. Same thing here, ready to form a bond. Same thing down here, ready to form a bond. Okay? What can it form a bond with? Okay, don't worry about what it can form a bond with. I'm just going to call it R, which is very arbitrary. Okay, don't worry about R, just worry about C, which is carbon. Happy at 4. This R can be anything. It could be the same atom. It could be a different atom. It could be a bunch of atoms. We don't care. I don't care. I don't want you to care. It could be R1, which is different from R. It could be R2. Okay. But I just want you to realize carbon is happy at 4. All right, so count with me here. 1, 2, 3, 4. Okay. Out of those 4. Okay, 1 is given by carbon. 1 is given by carbon. That's 2. 1, 2, 3, 4. Okay. All right, I'm going to replace this R. Again, you don't worry about the R. Okay? Just worry about the carbon, the first rule. I'm going to replace this R with just the very simplest atom. What's the very simplest atom in the periodic table?
Hydrogen.
Okay, very good. Okay, so hydrogen. And this molecule is called methane. You don't have to know that, but methane. Okay, so this is the structure of methane. All right, count with me here. Carbon, 1, 2, 3, 4. Trust me, there's going to be a lot of counting. Okay, you'll hate me at the end of this semester. All this counting we have to do. Okay? You'll get nauseated with the counting. All right. How many electrons are around the carbon? How many total electrons? Okay. 1 is it from the carbon? 2, 3, 4, 5, 6, 7, 8. Okay, total, because this is shared. Hydrogen gives 1, carbon gives 1. Okay, so out of the 2, 1 belongs to carbon, the other one belongs to whomever, whatever. Okay, we only worried about carbon. Okay, so count with me. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we say carbon has an octet, 8 around it. Okay, octet. Okay, that's called the octet rule. Try. You don't have to, because sometimes there's expanded octet, but you try to get 8 around it. You try. Is carbon happy? 1, 2, 3, 4. What is carbon happy at? 4. Okay. Now, does it always have to be a double bond? Or, I mean, does it always have to be a single bond? Okay, how can you achieve 4? Okay, you can achieve 4 with a double bond. Anybody here in anatomy or what is that? Physiology? Okay, wow. Okay, I've never had an anatomy class, so you are definitely above me in that regard. But in anatomy, they use something called formaldehyde. Have you heard of this molecule or chemical formaldehyde?
No.
Okay. Well, formaldehyde is used to preserve the specimen. Okay, they use it to preserve the tissue. Maybe Savannah knows about it, or definitely your anatomy professor knows about it. So formaldehyde has this structure. Oh, has this formula, I'm sorry, it has this formula, CH2O. Okay, how will you draw this? How will carbon get 4? A double bond. Very good, Zachary. Okay, a double bond with whom? This you may not know, but if you were to guess, a double bond with whom? Hydrogen, which is the most simple atom, or oxygen? Okay, it will be oxygen. Okay, oxygen is going to have, don't worry about the oxygen. What are we focusing on? Carbon. Okay, let's look at the carbon now. Count with me. 1, 2, 3, 4. Is carbon happy? Yes. What are the total, okay, around the carbon shared? Okay, 1, 2, 3, 4, 5, 6, 7, 8. So this carbon here satisfies the octet rule. Not everything will satisfy the octet rule, by the way. Okay. So here, the central atom, I want you to know this term also, central atom is carbon, and it satisfies the octet rule, which is 8 around. How do we get 8? Let's do it again. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so here, is carbon happy? Yes, because it has 4. Can carbon make 4 using a triple bond? Okay, the answer is yes. Okay, there's something called acetylene. It's an acetylene torch. Okay, let me give you the formula for acetylene. Okay, how will carbon get 4 around each carbon? When there's 2 carbons, each one gets 4. How will you get that?
Triple bond with carbon and then H on the other side, each side.
Sounds like you've done this before. A triple bond with the carbon, and what's on the other side? Each side? Hydrogen. Very good. Excellent job. Okay. Okay. Let's look at, we have 2 carbons here. Let's just look at one of them. Let's just look at one of them. Okay, this carbon, count with me. 1, 2, 3, 4. Is this carbon happy? Yes. How many total? Total electrons, shared and unshared. How many total? 1, 2, for this carbon here. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Okay, we're only talking about carbon now. Okay. I'll talk about H definitely later. Okay, what about this other carbon, the second carbon? Okay, is it happy? I'm talking about this carbon here. Okay, ready? 1, 2, 3, 4. How many total electrons around this carbon? Okay, count with me. 1, 2, this is shared. 3, 4, shared between this carbon and that carbon. 5, 6, 7, 8. So this carbon also, along with that carbon, satisfies the octet rule. And is it happy? It is happy. Why is it happy? It has 4 bonds. It could be a double bond, a single bond, or triple bond. Okay, so this carbon is happy. Okay, anytime you see carbon, try to get 4 around it. Okay, try to get 4 around it. Okay, 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4 for that carbon. Triple bond can only happen between carbon. No, you can get triple bond between carbon and nitrogen and other things. Yeah. All right, rule number 1. Okay. I think in this lecture we'll just talk about rules, and then Thursday we'll just start playing with these rules and playing the game. All right, let's do rule number 2. This is going to be nitrogen. Nitrogen is happy at 5. Okay, so here is how we'll do our nitrogen. All right, nitrogen, ready? 5 valence electrons. Okay, 1, 2, 3, 4, 5. Okay, 5. So lo and behold, nitrogen on the top, it doesn't matter if it's the top or bottom, I'm just drawing it like that. But nitrogen has what's called a lone pair. You see that? Where's the lone pair? Is that the top or the bottom or the sides? Okay, lone pair. So this electron is ready to form a bond, okay? Okay, anything. I'll just call that anything R. R is just a collection of atoms. It could be just one atom. It doesn't matter. Okay, it could be the same R here, or it could be something different. It could be the same or something different here. Let's not worry about the R. Let's focus on the nitrogen. Okay, so this is how nitrogen can be. Let's replace R with the most simplest element. What's the most simplest element? Okay, let's replace it with hydrogen. This is NH3. Okay, anybody know what NH3 is? Ammonia. Okay, and this is the structure of ammonia. All right, I want you guys to count with me. All right, is this nitrogen happy? Is this nitrogen happy? We're going to call nitrogen the central atom. Is this nitrogen happy? All right, ready? Count with me. 1, 2, 3, 4, 5. What is nitrogen happy at? 5. What's the total number of electrons around this nitrogen? The total. Okay? Shared and unshared. Okay, ready? Count with me. Shared and unshared to total. 1, 2, that's shared. 3, 4, 5, 6. This belongs to nitrogen. 7, 8. Does this satisfy the octet rule? The answer is yes. Is nitrogen happy? Yes. Let me give you another example. There's examples where nitrogen can get a double bond, but let me give you an example where nitrogen has a triple bond. Okay. Have you heard of hydrocyanic acid? Okay. When we did the nomenclature lab way back when, okay, week 2 or something, there was hydrocyanic acid. It has the formula HCN. Okay. HCN. Not HCl, that's hydrochloric acid. This is HCN. Okay, what would be the structure of this? Okay, let's make carbon our central atom. So how would you do it then? Carbon, what would carbon? Carbon loves or needs or desires what number?
4.
4. How will it get 4?
3 was N and 3 was N.
And what will nitrogen have? 5. But what will nitrogen also have? Okay. All right. This is all about nitrogen. Okay. So let's talk about nitrogen. Let's see if this nitrogen is happy. Count with me. Okay. 1, 2, 3, 4, 5. This nitrogen is happy at 5. So this nitrogen is good. What about the octet rule? Okay, ready? 1, 2, 3, 4, 5, 6, 7, 8. So this nitrogen satisfies the octet rule. Okay? So nitrogen has to be happy at 5. Carbon has to be happy at 4. We'll go over examples where nitrogen will need a double bond, but we'll do that later because that's a little bit advanced. All right, for now, I just want you to know nitrogen is happy at 5. Okay, rule number 3 is oxygen. Oxygen is happy at, if you were to guess, how many valence electrons oxygen would be happy at? Nitrogen is happy at 5. Carbon is happy at 4. Oxygen is happy at 6. Just focus on this a little. Oxygen happy at 6. what does that mean? Oxygen is happy at 6. Okay, so count with me here. 1, 2, 3, 4, 5, 6. I'll just keep it top and bottom. So oxygen, unlike nitrogen, has how many lone pairs?
2.
Just waiting for this to zoom, so bear with me, please. Okay, oxygen has 2 lone pairs. Okay. All right, so this electron here, let's pretend there's a bond going there. Okay, it can be anything. I'll call that R. Same thing here. It can be anything. We'll call that R. And then we'll have our 2 lone pairs. Okay, let's replace R with the most simplest element in the periodic table you can think of. What would that be? Okay, let's just replace the R. We can replace it with anything, but let's just be simple and replace it with hydrogen. So when we do that, what will we get? H2O. And what do we all know H2O as? Okay, our favorite substance, water. I think I'll take a sip of this right now. All right, count with me here on this oxygen. Is this oxygen really happy? Let's find out. Count. 1, 2, 3, 4, 5, 6. Okay, this oxygen is happy. What about the total? All the electrons surrounding the oxygen that is shared or by itself belonging to oxygen exclusively. Okay, this is the octet rule. Okay, ready? 1, 2, 3, 4, 5, 6, 7, 8. So this oxygen is not only happy, but it satisfies the octet rule, which is phenomenal. All right, let's do another example here. Remember the example from anatomy lab? What's that chemical? They put all the tissues in? Formaldehyde. So formaldehyde has this formula and this structure. All right, there's all right, only we're going to focus on the oxygen here. Okay, we're only going to focus on the oxygen. Okay, ready? Is this oxygen truly happy? Right? 1, 2, 3, 4, 5, 6. What is oxygen happy at? 6. Okay, so it's happy. But what about the octet rule here? Okay, you count everything. Those that belong and those that are shared with the atom focused on, and this is oxygen. Ready? 1, 2, 3, 4, 5, 6, 7, 8. So this satisfies the octet rule. Okay. So oxygen satisfies the octet rule and is happy. Carbon satisfies the octet rule and is happy. This is great. Okay. All right, let's move on to rule number 4. Fluorine, chlorine, bromine, iodine. These are the halogens. Okay. And they're happy at 7. Happy at 7. Okay. All right, let's just pick fluorine as an example, okay? count. Okay, 1, 2, 3, 4, 5, 6, 7. Okay, so here we're going to have 3 lone pairs. Okay, the halogens. 1, 2, 3. So same thing with chlorine, bromine, iodine. I'll just do chlorine. It's the same thing for Br, bromine, and iodine. 3, 4, 5, 6, 7. All right, so this 1 electron on the fluorine or the chlorine or all the other group 7, okay, I'm going to let it form a bond. Okay. Okay, it can be with anything. Same thing with the chlorine. Okay, so what's the simplest, most easiest element in the periodic table in terms of least complexity? Hydrogen. So let's replace the R with hydrogen. And we do that, we will get, I'll just flip it. Okay. All right, I get hydrofluoric acid. Okay, hydrochloric acid, HCl and HF. Okay, so let's look at the fluorine with me. All right, ready? Let's see if this fluorine is happy. Okay, here we go. 1, 2, 3, 4, 5, 6, 7. Okay, is this fluorine happy? Yes. Okay. Is this fluorine and chlorine satisfy the octet rule?
Yes.
All right. Count everything. This is shared, so it belongs to fluorine just as much as it belongs to hydrogen. 1, 2, 3, 4, 5, 6, 7, 8. So the octet rule is also satisfied. So before I move on to the next rule, there's something about HCl, HF, and H2O that I'd like you to recognize. Number one, the first thing I want you to recognize is that, remember from chapter 8, there is a region of these elements in the periodic table that are known as electronegative. Okay, do you remember that term, electronegative? Electronegative. So let's go back to oxygen here. Okay, it satisfies the octet rule. 1, 2, 3, 4, 5, 6, it's shared. 7, 8, it's shared. But this HO bond is not really equal sharing. Okay, this is an unfair fight. Why is that? Okay, because this concept of electronegativity. This bond and sharing between H and fluorine is not equal 50-50. Okay, sorry, we're not 50-50. Okay, same thing with the Cl. Okay, because of electronegativity. What happens is that this oxygen is going to pull. So we're going to draw a little line, and we're going to draw an arrow to create a tail. There's my tail. And it's pulling like a vacuum cleaner. It sucks the electron density like a vacuum cleaner. So this is going to be partial negative because these are electronegative elements. If this sucks on this electron bond, electron density, and makes it partial negative, what will this hydrogen be? Obviously. Okay, partial positive. Okay, it's the same with the other end. This oxygen here is pulling, 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 tugging, pulling. It's a tug of war on sharing this bond, and it's winning. So this oxygen is pulling, pulling, and it's the same on the other end as well. Okay. and these are called polar molecules. It's the thing we study in Chem 2 at the very beginning of Chem 2, polarity. And this is the basis behind hydrogen bonding if you study biology. Biology majors? No biology majors, okay. Well, in biology class, they make a big thing about hydrogen bonding. All right, so we call this polar. Okay. Okay, this is the symbol delta. Okay, it's the Latin letter for delta. Okay, delta. And then we can put it delta positive or delta negative. Okay, this is the same thing over here. Okay, the fluorine is going to pull, and that's partial negative. This is partial positive. The Cl is going to pull. Okay, partial positive. Okay, again, just like with water, H2O, these molecules are polar. Okay, so when you're doing your analysis, if you look at the periodic table, there's always this region here that wants to be noble. It wants to be like the noble gases. So they have this incredible electronegativity, this pulling power. That's going to pull on that bond. So it's not a equal sharing, Husong. Okay, they don't share. Okay. It's not an equal sharing. Okay. All right, so just want you to know oxygen and the halogens, they're going to be electronegative. Okay, let me give you one more example of this. Okay, let's look at chlorine here. CCl4. Okay, how would you draw the Lewis structure for CCl4? Okay, C in the middle, that's definitely correct. And then what else? Okay, 4 Cls around it. What else will you have on the outer Cls? The 3 lone pairs. So this would be the structure of carbon tetrachloride. So what do you think? Do you think carbon tetrachloride would be polar? This is a tricky question, and I just want to see if you guys can get it right. If you don't, that's perfectly fine, because it's a little tricky. Okay, what do you think this Cl is going to do that it does here? Pull. Very good. Okay, what will this Cl do? Pull on that carbon, so it's not a 50-50 sharing. What will this Cl do? Pull the other way. And then what will the Cl at the bottom do? Pull. So is this polar or non-polar? Okay, this pulls with a partial negative, but what cancels it out? What? The downward cancels it out. So they cancel each other. What about the one on the left? It's pulling this way. What will the Cl on the right do? Pull. Will they cancel each other? So this pull cancels that pull. This up pull from the electronegative Cl will cancel the up pull. And then the down Cl from the electronegative Cl will cancel. The up cancels down, left cancels right. And this is non-polar. We'll talk about this in our final lab next week, polar versus non-polar, but this is definitely non-polar. Okay, so the poles can literally cancel each other out. All right, let us do, let's see here, 1, 2. Okay, we'll do 3 more rules and then we'll start hitting the ground with some examples. All right. So carbon is happy at 4. What do you think silicon would be happy at? 4. Nitrogen is happy at 5. What do you think phosphorus would be happy at? 5. Oxygen is happy at 2. Sulfur -2. Sulfur would be happy at 6. Okay, 6. Fluorine is happy, as we said, all the halogens are happy at 7. Okay, the noble gases are happy at, except helium. Okay, the noble gases are going to be happy at 8. This is very rare. You won't see this, and we will not see this very much, but the noble gases are going to be happy at 8. Okay. I think we know this. They have 8 electrons around their shell. At 8. Okay. I'll just use xenon as an example. All right. So completely filled shells, which makes them kind of unreactive. Okay. 1, 2, 3, 4, 5, 6, 7, 8. Now, even though, so this is rare, because I just told you noble gases are not very reactive, but there is something, and if you look at your textbooks, you'll see this, there is something called xenon tetrafluoride. Okay, let's do this one as an example of a Lewis structure with a noble gas. This is called xenon tetrafluoride. Tetrafluoride. All right, after this we'll do 2 more rules and then we'll hit the ground running with lots of examples. All right, what is xenon happy at? 8. What is fluorine happy at?
7.
Okay, 7. But we have 4 fluorines, so we have 28. Bless you, 28, right? Why is it 28? Because they're 4. Okay, so 8 valence electrons, 28 valence electrons. How many total valence electrons for the whole XEF4? Okay, so our job is to get 36 valence electrons around xenon F4. That's our job. Okay. So what do you think the central atom will be? Would it be xenon or would it be fluorine?
Xenon.
Okay, it makes more sense for it to be xenon because you have fluorine, then you have a fluorine xenon. It's just messy. Okay, we want to be simple, xenon. And what's going to be bound to the xenon? How many fluorines? 4. So here's 1 fluorine, 2 fluorine, 3 fluorine, 4 fluorine. Okay. What do we know around how many valence electrons around the halogen, like a fluorine? How many? It's 7, but how many valence electrons? How many lone pairs around the halogen? 3. 3, right? So what should we do here? All right, so let's count the total electrons here. All right, remember we got to do a lot of counting, so count with me. All right, let's count. All right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. But we need 36. 32. Where will 33, 34, 35, and 36 go? They can't go on the fluorine. Where will they go? They'll go on the xenon. Okay, they will go on the central atom. Okay, now, do we have 36 valence electrons? Yes. Okay. Let's do the happy and octet rule. Okay. Okay. All right. So let's see here. Fluorine. Ready? Is it happy? 1, 2, 3, 4, 5, 6, 7. 7. Okay. Happy. Octet rule. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Does it have octet? Yes. Shall I do it on this one, or you already know? You want to do it again? I mean, these four are all the same. Single bond F, single bond. Want to do it again? Yes or no?
No.
All right, I'll take that no. Okay, this fluorine is the same environment as this fluorine, which is the same chemical environment of this fluorine, which is the same chemical environment of this fluorine. If you take higher chemistry classes, they call them equivalent. Okay, so they look the same, they behave the same on the instrument, okay, analysis. But the xenon here is very interesting, so pay close attention. I request you. Okay, let's see if this xenon satisfies the happy rule, happiness. What is xenon and all noble gases happy at? 8. They achieve the octet. All right, ready? 1, 2, 3, 4, 5, 6. Okay, I'm doing octet rule. Okay, we'll do octet. Okay, let's do happy again. Okay, ready? 1, 2, 3, 4. Yeah, thank you. That helped me. Is this xenon happy? Yes. Now let's do the octet rule. Okay, count with me. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay? So does this have an octet? Okay, so this is called an expanded octet. Is it happy? 1, 2, 3, 4, 5, 6, 7, 8. Yeah. Happiness is more important. So to get it happy, it does an expanded octet. Okay. So do you always have to satisfy the octet rule? Yes or no?
No.
Okay, there can be something called, so this one takes up, what is it, 12?
Yep.
12. Okay, so don't always be so hard and fast and set on the octet rule. Okay? Yes, sir, go
Why
ahead.
does the electron goes around the C9, but 2 on each side?
You can put it up and down, it doesn't matter. Yeah, I just put it like that.
Because I thought you have to follow the rule. You have 1 on each side, and then you can add 2 on when you're counting the electron or join.
I mean, when you do that, eventually you'll have, they'll be paired like this. Yeah. Okay. So this is called xenon tetrafluoride. If you understand this, then I think that's good. Okay. That's really good. Okay. But for now, if you don't understand it, that's okay. All right. Let's do a couple of more rules here. Hydrogen is happy at...
What?
Okay. Hydrogen is happy at 1. Okay. right, so very simple hydrogen. It just has one electron, okay? All right, so let's replace that hydrogen with, what's the simplest element in the periodic table? Hydrogen, okay? So this would be what hydrogen is like, H2. All right. What was that chemical again in anatomy class? Formaldehyde. Okay, let's go over formaldehyde again. Which was at CH2O. And what is its structure? Okay. Let's look at the hydrogens here. All right. Is this hydrogen happy? 1. What is hydrogen happy at? 1. What about this hydrogen? 1. Okay, what is the octet rule for hydrogen? There's no way it can get 8. What is the octet rule? 1, 2. So what is the octet rule for hydrogen? 2. Okay, 2. So here you can have an expanded octet for xenon, and you can have an expanded octet for many other Lewis structures. But for hydrogen, will it get 8? No. Okay, so the octet rule for hydrogen is what number? 2. Okay, so there's a lot of don't be so hard, fast, and set on the octet rule always being 8. There's expanded octet, and then some things just no matter what cannot get 8. And hydrogen, being the most simplest element in the periodic table, simply cannot get 8. So the octet rule for hydrogen is 2. That's it. Okay. Again, I'm going to repeat it over again, just like you have to count for here till the end of the class, end of semester. Okay, the octet rule for hydrogen is 2. Okay, don't always be trying to get 8. Now I'll tell you this. You want an expanded octet in the central atom. Okay, there's a lot of rules in this game. It's a complicated game. Okay, you want the expanded octet in the central atom. You don't care about the outer atoms. The outer atoms should be according to the rules. But this expanded octet happens where? In the central atom. Okay, it can only accommodate that in the central atom. Okay, so 3 little subsets into our rule. Okay, how about H2O as an example? Water. Okay, we mentioned that it's polar because the oxygen is electronegative. What about this hydrogen? Happy? 1. Okay, hydrogen happy at 1. And what is the octet? 1, 2. Okay, so the octet rule is satisfied for the hydrogen. Same thing with that one there. All right, I'm going to give you one last rule, and then we'll hit the ground running and just do the examples. Okay, my last rule for you guys is aluminum and boron. Okay, this is the last rule, aluminum and boron. They are happy at 3, right? Okay, so we got 1, 2, and these guys are happy at 3. Boron and aluminum is what I want to talk to you guys about. Okay, boron is the element B, aluminum is the element Al, and they are happy at 3. Okay. So 1, 2, 3. Boron, 1, 2, 3. Okay. So let's replace aluminum. I'm sorry, let's replace this dot with it forming a bond. Okay. And then what's the most simplest element in the table? Okay, let's just replace it with a very simple hydrogen. So this would be aluminum trihydride and boron trihydride. All right, is this aluminum and boron happy? Okay, 1, 2, 3. What is the octet rule for aluminum and boron? Very good. 1, 2, 3, 4, 5, 6. So don't be so hard and fast and set on the octet rule, always being 8. Hydrogen, the octet is 2, and for these guys, the octet is 6. And then there are some central elements that could have an expanded octet. So this is the second thing. The octet rule for aluminum and boron is 6. So those are our ground rules, and then what's the goal? Okay, the goal. Our goal is to win, right? Well, our goal is to get the right structure. Okay, so our goal here is to, in this game that we're going to call Lewis structures, our goal is to minimize formal charge. This is the most single, absolute, 100% one and only goal of this whole game, and that is to minimize formal charge. Okay, so what is formal charge? Okay, I'm going to call formal charge FC. Formal charge is what we want to minimize, is happy. Okay, minus the total number of electrons around the atom. That is the goal, okay? We want to get this as low as possible. Okay, that's why you can have an expanded octet. Okay, that is why you can have octet of 6 for aluminum and boron. This is why hydrogen only has an octet of 2. Okay, because of formal charge considerations. Okay, formal charge. So let's look at some examples here. Okay, what is that molecule, that chemical that we have to always deal with in anatomy lab, for those of you that are going to be in anatomy or doctors or whatever you're going to be, pathologists? Okay, formaldehyde. Let's look at formaldehyde again. And now let's do our goal here, and that is to minimize formal charge. First of all, what is the total charge on formaldehyde? Do you guys see a charge? Do you see any pluses or minuses? Okay, the charge is 0. Okay, let's look at the structure here. Okay, let's look at the central atom carbon. All right, let's do the formal charge. Ready? Count with me. 1, 2, 3, 4. What is carbon happy at? 4. What's 4 minus 4?
0.
The formal charge of that carbon is 0. Oxygen, we're going to do formal charge, not the octet. This is not the octet. This is formal charge. Ready? 1, 2, 3, 4, 5, 6. Let's do it again. 1, 2, 3, 4, 5, 6. What is oxygen happy at? 6. What's 6 minus 6? Formal charge on this oxygen atom is 0. Hydrogen, same thing with that hydrogen. Ready? 1. 1. What is hydrogen happy at? 1. What's 1 minus 1?
0.
So the total, that's the same for this hydrogen also, by the way. Okay, so the whole charge is 0. The whole thing here is 0. Okay, this is the best structure. Not only that, the formal charge are all zeros, and the whole thing here is 0, but every atom here has an octet, which is even more splendid. Okay. So this is how we do it. Okay. All right, let's do a couple of examples here. Let's get in here. All right, we got about 10 or so minutes. Let's just have some fun and do some examples. Okay, so what's the goal here? Minimize what? Formal charge. All right, let's look at, remember in your flashcards that we did almost 13 weeks ago, there was a ion in your flashcards called hydroxide ion. You guys remember this? Okay, let's draw the Lewis structure of hydroxide ion. Okay, what is oxygen happy at? 6. What is hydrogen happy at? 1. What does that minus sign from hydroxide mean? Yes, the -1 means -1, but what does it mean? Like, in terms of an electron, did it gain an electron or lose an electron? Okay, so our goal is to get 8 valence electrons around the hydroxide ion. 8. All right, so how will we do that? Okay, so we have an oxygen here. What is it bound to? Hydrogen. Okay, so that's 1, 2. Where will 3, 4, 5, 6, 7, and 8 go? Around the oxygen. So 1, 2, 3, 4, 5, 6, 7, 8. So we have an oxygen bound to a hydrogen. And there are 2 things we have to look at when we do Lewis structures. One is octet, and the other one is what? The goal? Minimize the formal charge. Yes, Emily. Okay, so let's do octet rule here for hydrogen. 1, 2. Octet rule satisfied. Okay. Let's do formal charge for this hydrogen. Okay, 1. 1. What is hydrogen happy at? 1. What's 1 minus 1? 0. Okay, the octet rule is good here. Okay, now let's do this oxygen. Okay, let's do the octet rule. Okay, we count everything for the octet rule. Okay, everyone count with me. Let's count together. 1, 2, 3, 4, 5, 6, Octet rule is satisfied. Okay, what about formal charge? Okay, everyone count with me. Formal charge. 1, 2, 3, 4, 5, 6, 7. 7. 7. What is oxygen happy at? What is 6? Oxygen happy at 6. What's 6 minus 7? So the formal charge is -1. That's where the -1 comes from. The -1 is actually on the oxygen. So in your textbook or whatever, really it's on the oxygen. Textbook or any book that depicts it like this is not an accurate depiction because the formal charge is really localized on the oxygen. Okay? Once again, let's do it again. 1, 2, 3, 4, 5, 6, 7. Oxygen happy at 6. 6 minus 7 is -1. This oxygen carries a formal charge of -1. We already know there's a -1 in our problem. Right, this is called the hydroxide ion. All right, let's do CO2. Okay, this is called carbon dioxide. All right, what is carbon happy at?
4.
Okay, what is oxygen happy at? Okay, but how many oxygens do we have? 2. So 4 plus 12 is 16. So we need to get 16 valence electrons around carbon dioxide. Okay, how will we do that? Okay, very good. Gerardo is right. We'll put carbon in the center. And then what else? A double bond with each oxygen is correct. Anything else that's missing? Where?
Oxygen.
How many?
2 each.
What about this one? Same thing. Okay. Let's count our total electrons just to make sure we're at 16. Okay, count everything. Okay, the total should be 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 valence electrons. Okay. All right, shall we do the octet and formal charge for this carbon? Okay. I told you you're going to get tired counting, and we're just in day 1. Okay. When is Thanksgiving? 2 weeks. Okay. Do a lot of counting. And then after that, more counting. All right. Octet rule for this carbon here. Octet rule for the carbon. 1, 2, 3, 4, 5, 6, 7, 8. Carbon, formal charge 1, 2, 3, 4. What is carbon happy at? 4. What's 4 minus 4?
0.
The formal charge on this carbon is 0. Oxygen, which is the same whether it's this oxygen or that oxygen, so I'm just going to do it one time because they are equivalent. All right, octet. 1, 2, 3, 4, 5, 6, 7, 8. Octet rule is great. What about formal charge? Okay, 1, 2, 3, 4, 5, 6. What is oxygen happy at? 6. What's 6 minus 6?
0.
The formal charge on this is 0. It's the formal charge the same on that oxygen because, they're one and the same. You just flip it back and forth. All right, let me ask you this. Is this is this whole CO2 molecule polar or nonpolar?
Non-polar.
Okay, why is it nonpolar? That's the right answer. Very nice.
They cancel each other.
Okay. The poles from the oxygens cancel on both sides. Okay. So this would be an example of something that's non-polar. All right, let me do one more. All right, we still haven't done the 3D part of this. Okay, this is just flat. Is this how CO2 looks like? Okay, there's a three-dimensional aspect to this, which we will do this week and next week, and your lab will do together next Tuesday. All right, let's do our last one for today, ammonium ion. It's not NH3, which is ammonia. This is NH4 positive, which is ammonium. Okay, what is nitrogen happy at? 5. What is hydrogen happy at? But how many do we have? 4. And what does that E minus? What does that plus sign mean? 1 electron must be removed. Very good. So total, how many total electrons are we looking at here? 5 plus 4 is 9. 9 minus 1. Our job is to get 8 valence electrons around the ammonium ion. 8. Okay? Okay, so what will be the central atom here? Hydrogen. 4 hydrogens. I would make nitrogen the central atom, yeah. And then what's bound to it? The 4 hydrogens. All right, what is the octet rule for each hydrogen? We'll just do 1 because it's the same for the other 3. All right, 1, 2. Is that good? Okay. Formal charge for this hydrogen here. 1. What is hydrogen happy at? 1. What's 1 minus 1? The formal charge on this hydrogen, that, and that, and that are all 0. All right, nitrogen. Let's do the octet rule. 1, 2, 3, 4, 5, 6, 7, 8. Octet rule is really good for that nitrogen. Let's do formal charge for this nitrogen. 1, 2, 3, 4. Once again. 1, 2, 3, 4. What is nitrogen happy at? What's nitrogen happy at? 5. Okay, 1, 2, 3, 4. Everybody now, what's nitrogen happy at? 5. What's 5 minus 4? 1. So this will have a formal charge of plus 1.